At the very center of the Milky Way, something invisible has been shaping everything for billions of years. It doesn't shine. It doesn't roar. It doesn't announce its presence. And yet, millions of stars move as if bound to an unseen master. This object is known as Sagittarius A, a supermassive black hole 4 million times the mass of the Sun. But here's the strange part. We didn't find it by seeing it. We found it because the universe around it had no other explanation. So how do you discover something that never appears, never shines, and never shows you the present? That question is where this story begins. Sagittarius A is a supermassive black hole located at the very center of the Milky Way galaxy. It is not a theory placed there for convenience, but a conclusion forced upon astronomy by decades of observation. This object lies roughly 26,000 light-years away from Earth, embedded deep within the dense core of our galaxy. That distance alone already tells us something important about how we encounter Sagittarius A. We are not observing it as it is now, but as it was tens of thousands of years ago. Sagittarius A contains a mass roughly 4 million times greater than that of our Sun. To place that in perspective, this enormous mass is confined within a region smaller than the orbit of Mercury. Yet, despite this immense mass, Sagittarius A does not shine. It emits no visible light and produces no steady glow that telescopes can directly capture. This often leads to a common misconception about black holes. Sagittarius A is not a cosmic vacuum cleaner pulling in everything around it. The stars near the galactic center are not being swallowed one by one. Instead, they move in stable but extreme orbits, governed by an unseen gravitational anchor. These stars act like test particles, tracing the shape of an invisible force. Over years and decades, astronomers track their motion with extraordinary precision. Some of these stars complete full orbits in just a few decades. Their velocities reach several thousand kilometers per second. No cluster of ordinary matter could hold such stars together without tearing itself apart. The only explanation that fits all observations is a compact object with enormous mass. Not a star, not a cluster, not an exotic cloud of matter, a supermassive black hole. What makes this conclusion remarkable is how indirect it is. Sagittarius A was not discovered through an image. It was discovered through motion, timing, and mathematical necessity. Astronomers did not see the object itself. They saw how space around it was forced to behave. Every orbit that closed, every velocity that exceeded expectations, pointed to the same conclusion. Remove Sagittarius A from the equations, and the galaxy's core no longer makes sense. The mathematics break. The motions become impossible. In this way, Sagittarius A is known not because it announces itself, but because nothing else can replace it. It is an object defined more by its consequences than by its appearance. An object we cannot see, yet one that the galaxy cannot do without. If Sagittarius A has been shaping our galaxy for billions of years, why did it take humans so long to realize it was even there? The reason Sagittarius A remained hidden for so long is not because it was subtle, but because our position in the galaxy is deeply limiting. From Earth, we observe the Milky Way from within its disk, looking inward through layers of gas and dust. These clouds are not thin or transparent. They are dense, cold, and extraordinarily effective at blocking visible light. For optical telescopes, the galactic center is almost completely obscured. Even the brightest stars behind this veil are dimmed or erased from view. For centuries, this limitation shaped what humans believed the center of the galaxy looked like. It appeared calm, unremarkable, and largely empty. Sagittarius A itself offered no help in revealing its presence. Unlike many black holes, it does not blaze with energetic radiation. It does not produce a luminous accretion disk visible across the galaxy. For most of its existence, Sagittarius A has been remarkably quiet. With no light to trace and no dramatic outbursts to announce itself, it left astronomers with nothing obvious to detect. The breakthrough came only when astronomy learned to see the universe in new ways. Radio astronomy was among the first to penetrate the galactic dust. Radio waves pass through clouds that completely block visible light. When astronomers pointed radio telescopes toward the galactic center, something unexpected appeared. A compact and persistent radio source, fixed at the galaxy's core. This source was later named Sagittarius A. Still, a radio signal alone was not enough to confirm its true nature. The decisive evidence emerged with the rise of infrared astronomy. Infrared light can slip between dust particles that scatter visible wavelengths. With this capability, astronomers finally began to see stars orbiting extremely close to the galactic center. These stars did not drift gently. They raced along tight, curved paths at astonishing speeds. Over time, their repeated motion told a consistent story. Something massive was there. Something invisible. Something unavoidable. Humans did not discover Sagittarius A by seeing it directly. They discovered it because the universe left no other explanation. The evidence accumulated slowly, patiently, across generations of instruments and observers. At no point did Sagittarius A reveal itself all at once. Instead, it cornered science through consistency. Every new observation reduced the space for doubt. In the end, astronomers were not convinced by spectacle, but by necessity. But there is one question that needs to be clarified. Are we truly observing Sagittarius A? Or are we only ever reconstructing a story written 26,000 years in the past? When we ask whether we are observing the present or the past of Sagittarius A, the answer is precise and unavoidable. Sagittarius A lies approximately 26,000 light-years away from Earth. That distance means every signal we receive began its journey long before modern human civilization existed. Light does not arrive instantly. It travels at a finite speed, carrying information forward through time. As a result, every image, every measurement, every photon we collect from Sagittarius A is already history. We are not seeing what exists there now. We are seeing what existed there 26,000 years ago. This time, delay cannot be corrected or bypassed. There is no instrument powerful enough to reach beyond it. There is no method to check the current state of Sagittarius A in real time. Even if Sagittarius A were to change dramatically today, we would not know for millennia. This creates a fundamental separation between the object and the observer. Sagittarius A exists in the present, but we can only ever access its past. In this sense, we are not observing the object itself. We are observing the consequences it left behind in space-time. The bending of stellar orbits, the acceleration of stars near the galactic center, the structure of motion that persists long after the light has departed. Sagittarius A is therefore a real and present entity that is never simultaneous with our observation of it. It is always slightly ahead of us in time. Science must work within this constraint. It must accept that some objects can be measured with precision, yet never witnessed as they are now. And this limitation is not a flaw of technology. It is a consequence of how the universe itself is structured. So, what does it mean for science when the closest supermassive black hole can never be seen as it is right now? When science cannot observe the present directly, it does not stop. Instead, it adapts its methods to work within the limits imposed by the universe. In the case of Sagittarius A, this means accepting that direct images are not the primary source of knowledge. The data that matters most is not visual, but behavioral. Science studies how stars move, how gas responds, and how space itself is shaped. These patterns form a model, not a picture. From this model, Sagittarius A emerges as an unusually quiet, supermassive black hole. Unlike the active black holes seen in distant galaxies, it does not dominate its surroundings with light. There is no bright accretion disk blazing across space. There are no powerful jets launching material at near light speed. Sagittarius A appears calm, almost dormant. Astronomers describe this state as a resting phase. The black hole is still massive and still dominant gravitationally, but it is consuming very little matter. Without a steady supply of gas and dust, there is little energy to radiate. This quietness does not mean inactivity. The gravitational influence of Sagittarius A remains constant. It continues to govern the orbits of nearby stars with precision. What changes is how visible that influence becomes to our instruments. Science therefore builds its understanding from consistency rather than spectacle. A quiet black hole still leaves a clear gravitational signature, and that signature can be measured, tested, and compared against theory. Over time, this indirect evidence becomes more reliable than a single dramatic observation. Sagittarius A teaches science an important lesson. Not everything that matters announces itself loudly. Some of the most influential objects in the universe reveal themselves only through patience and inference. And this brings us to another question. If Sagittarius A is mostly quiet and starved, what does a resting supermassive black hole actually look like? A resting supermassive black hole is not something astronomy can simply photograph and label. There is no definitive visual signature that announces its quiet state. In fact, the absence of dramatic light is precisely what defines it. This forces science to understand Sagittarius A in a fundamentally different way. Instead of images, astronomers rely on motion. Instead of brightness, they study velocity. And, instead of direct observation, they follow gravity. Every star orbiting near the galactic center becomes a messenger. Its path through space carries information about the invisible mass it responds to. By measuring these orbits with precision, science reconstructs the gravitational landscape. The tighter the orbit, the stronger the conclusion. Some stars swing so close to Sagittarius A that their motion leaves little room for interpretation. Their velocities rise and fall exactly as predicted by extreme gravity. No visible object can account for this behavior. At this point, mathematics enters not as a supporting tool, but as a necessity. The equations governing motion and gravity must close. They must balance. When scientists attempt to model the galactic center without a supermassive black hole, the equations fail. The predicted motions no longer match reality. Energy distributions become unstable. The system cannot sustain itself. Only when Sagittarius A is included does the mathematical framework become coherent. In this sense, the black hole is not assumed. It is demanded by the equations themselves. This is why astronomers often describe Sagittarius A as mathematically unavoidable. The data does not gently suggest its presence. It insists on it. Over time, repeated measurements reinforce this conclusion. Different stars, different orbits, different instruments all converge on the same result. The consistency becomes more convincing than any single observation. In the absence of images, coherence becomes evidence. This approach reflects a deeper truth about how science works. Science does not require visibility to establish reality. It requires predictability, consistency, and explanatory power. Sagittarius A satisfies all three. A resting black hole, therefore, becomes real not through sight, but through necessity. It is a solution that remains when all alternatives fail. And yet, this raises an important question about what we truly know. How much of our understanding of Sagittarius A comes from direct evidence, and how much comes from mathematical necessity? When we ask how far Sagittarius A influences the Milky Way, the answer is more subtle than simple control. Sagittarius A does not command the motion of every star in the galaxy. It does not dictate the path of our sun or the spiral arms far from the center. Most stars are governed primarily by the combined mass of billions of other stars. Yet this does not mean Sagittarius A is insignificant. Its role is not one of constant supervision, but of foundational influence. In the earlier stages of the galaxy's formation, Sagittarius A helped shape the inner structure. It acted as a gravitational anchor around which matter settled. Gas clouds fell inward. Stars formed in dense environments influenced by this central mass. Over time, this process established the core of the Milky Way. The influence of Sagittarius A is strongest near the galactic center. There, stellar orbits are tightly bound and highly sensitive to its gravity. As distance increases, this influence gradually fades. Far from the center, Sagittarius A becomes just one contributor among many. This gradient of influence reveals something important about its role. Sagittarius A is not the present ruler of the galaxy. It does not actively govern every interaction taking place today. Instead, it is better described as an early architect. Its greatest impact occurred long ago, when the galaxy was still taking shape. Once the structure stabilized, continuous intervention was no longer required. The galaxy continues to evolve, but along paths set early in its history. In this sense, Sagittarius functions more like a historical force than an active controller. Its presence shaped possibilities rather than outcomes. It defined the conditions under which the inner galaxy formed. After that, gravity and time did the rest. This perspective reframes how we think about influence in the universe. Power does not always mean constant action. Sometimes, it lies in having been there first. Sagittarius A may now be quiet, but the galaxy still carries the imprint of its early presence, which leads us to a final question about the reach of that imprint. If a single object can anchor the inner heart of an entire galaxy, where does its influence truly end? The influence of Sagittarius A does not end at a clearly defined boundary. There is no sharp line where its role suddenly disappears. Instead, its influence fades as structure takes over. Once the inner galaxy reached stability, constant intervention was no longer necessary. Sagittarius A did not need to keep acting to maintain order. Its early presence was enough. By anchoring matter during the galaxy's formative stages, it set conditions that endured. Stars continued to form, orbits continued to evolve, and structures persisted long after. The black hole did not guide every step. It defined the landscape in which those steps could occur. In this way, its influence is not measured by ongoing activity, but by lasting consequence. The Milky Way does not orbit Sagittarius A as a whole. Yet, its inner heart still bears the imprint of that central mass. This reframes how we think about causality in the universe. Not everything that shapes a system continues to act within it forever. Some influences are front-loaded into the beginning. After that, time and physics carry the structure forward. Sagittarius A belongs to this category. It is not the galaxy's present ruler. It is the reason the inner galaxy could become what it is. From this point, the question shifts. It is no longer about the black hole itself. It becomes a question about science, about how knowledge is built when direct appearance is impossible, about how certainty can emerge from absence, and about how the universe reveals itself without ever fully showing its hand. Sagittarius A does not need to be loud to shape the galaxy. It does not need to shine or announce its presence. It simply needs to exist, and everything else must adapt around that fact. This quiet influence reminds us that power in the universe is not always dramatic. Sometimes it is patient. Sometimes it is invisible. And sometimes it reveals itself only through what it leaves behind. If you want to continue exploring the unseen structures that quietly shape the universe we live in, you are invited to subscribe to this channel. Not for answers set in stone, but for questions that lead us closer to understanding. Because sometimes, the most powerful things in the universe are the ones we never get to see.